In this video, I'd like to continue our discussion about the Calc 1 review, and at the very end of the semester, we started talking about U substitution as a method to find the antiderivative of a complicated function. Well, if you recall, the U substitution is really the equivalent of the antiderivative form of the chain rule, and I say that it's the antiderivative of the chain rule because with our derivative rules, we use the chain rule when there's a function inside of another function, and that's exactly what's happening here. We have a function inside of another function, and we can use this U substitution method to undo that, if you will, to find the antiderivative. Now, first off, before I show this example, I'm going to note here that this is a bit of a different way of writing an antiderivative, or a definite integral in this case, in that the differential dx is written on top of the fraction, and that's okay. We see that from time to time. What that really is telling us is that we have the fraction 1 over 2x plus 1 cubed dx. And so they loosely just multiplied this 1 times dx over 1, and now we've got the fraction dx over 2x plus 1 over 3. So it might be easier for us to see this process by writing it this way, and that's what I've done here. What U substitution is going to allow us to do when it's possible, when it's available for us, is it's going to take a slightly more complicated equation and write it in a simpler form. So what I'm going to do is I'm going to say that we're going to let the letter U equal the entire equation 2x plus 1. And it would be nice if I just evaluate the antiderivative of 1 over u cubed. And I say that would be nice because we can actually find the antiderivative of 1 over u cubed. That's something that we've practiced a bunch of by now. The problem is that when we start changing variables around, we were using x to begin with, and now we're switching to the letter u. We also have to account for changes in the differential. So this is a differential relative to x. We're going to need some sort of differential relative to u, which we'll show you how to get that in just a second. But also these boundaries of integration are written in terms of x. This is saying that the area under this curve between an x value of 0 and an x value of 1 needs to be computed. Whereas down here, if we switch to the integral with the variable u, we're now talking about the position u. And the position of u is not the same necessarily as the position for x. So we're going to have to adjust for that as well. So first things first, we have selected the letter u to be equal to 2x plus 1 because that's going to be helpful for us to rewrite the equation. Well, as it turns out, the derivative of u with respect to x is easy to find too, and that's equal to just the number 2. If we take the derivative of both sides of this equation, we're left with du dx on the left and just the number 2 on the right. As I said a minute ago, our goal is to rewrite dx so that we have only a differential relative to u. So with a little bit of liberty, if you want to call it that, with our math here, this is part of our differential equation studies that we'll see this semester. I'm going to multiply both sides by dx, and that's going to allow the component to disappear from the right. And I now have the expression du equal to 2 times dx. Well, here again, I would like to replace dx, so essentially I'd like to get dx by itself over here, and I'm going to divide both sides by 2, or another way we can think of that is multiplying both sides by 1/2. And so if we multiply both sides by 1/2, we're now saying that the differential dx is equal to half of the differential du. So anywhere that I see dx, primarily in the first example, I'm now going to replace dx with 1/2 du. Whether you show that multiplication sign or not, it's not that big of a deal. Or if you place it here, that would be okay too. Okay, well that's interesting. All that did for us is it introduced a constant multiplier. So when I actually compute the definite integral, I can just move that 1/2 to the outside, compute the integral with my new boundaries, which I still haven't established yet, but I'll show you how to do that in just a second. And we're going to do that by finding the antiderivative of 1 over u cubed with respect to u. So we're actually in pretty good shape so far. The last little piece that we've got to square away is that this new graph, this new function, 1 over u cubed, is not the same as 1 over 2x plus 1 cubed. Those two are fundamentally different, but they can contain the same area under the curve as long as we adjust our boundaries here appropriately. And the clue here should fill you in on how that's to be done. We're just simply going to state what u is equal to in terms of x. Now, our upper boundary, I'm going to say u sub u, our upper boundary is simply the u equation, u equals 2x plus 1, where x is being substituted with the upper boundary of x from before. So this upper boundary here for u is going to be 2 times 1 plus 1, which equals 3. And the lower boundary of integration is 2 times 0 plus 1, because those were the boundaries of integration in terms of x, and we're using those x values to adjust our boundaries of integration in terms of u. So this lower boundary is 1. So what we would need to do from here is compute the antiderivative of, let me get this out of the way so it's not so messy, from 1 to 3 of 1 over u cubed du, and this expression is exactly the same as this expression. Or I should say the calculated results will be the same. Now, hopefully by now you're comfortable with finding the antiderivative and evaluating it at 1 and 3. So I'm not going to run through that process, but I will hopefully make my final claim here. If I use the calculus menu on this CAS-enabled TI Inspire, I can compute an integral. And this first integral that I'm going to compute is on the boundary from 0 to 1 on the fraction 1 over the quantity of 2x plus 1 cubed. And this integral is built relative to the variable x. So when I press enter here, we see that the area under this curve is equal to 0.22 repeating units. Now if I compute another integral, again using the calculus menu, this time we're interested in the boundaries from 1 to 3 of 1 over, actually I need to include this 1/2, so let me jump over here because we said there was a 1/2 multiplied by the integral of 1 to 3 of 1 over u cubed. Now I'll use the letter u since this calculator can handle it, relative to the variable u here. The claim is that this new integral, 1/2 times the integral from 1 to 3 of this function, is going to contain the exact same area as the integral from 0 to 1 of this function. So let's see what we got. And wouldn't you know it, they are exactly the same. A visual representation of this can be made as well. In the graph I'm about to show you, you'll see the blue graph that represents this function, 1 over 2x plus 1 cubed. And in the second function, you'll see 1/2 times 1 over x cubed. Now I have to use x because that's how our calculator builds its functions, but it'll represent the same thing. In this blue graph, again, our original function, the area under that curve is 0.2 repeating. And if our job was to find the area under that curve by using integration, what we're essentially doing is we're creating a new equation, as even though it may look and be positioned differently than the original, by adjusting the boundaries, in this case going from 1 to 3, the area underneath that new curve is exactly the same as the area under this one. So the area from 0 to 1 contained by this gray region and the area from 1 to 3 contained by this gray region are exactly the same. This red function has been used in place of the original. So let's take a look at another example. And remember, the goal of u substitution is to pick some sort of inner function that's derivative also exists elsewhere in the function. So in this case, if we allow u to be equal to 4 minus x squared, that's good, because the derivative of u with respect to x is going to be equal to 2x And if we divide both sides and move some things around, we've got du that's equal to 2x dx. Now, one of the problems that we have here is that I don't have a 2x dx, I just have a single x dx. And to help see that a little bit more clearly, we could, if we wanted to, rearrange some things. We've got 4 minus x squared times x dx. So we have an x dx, and we have a square root of 4 minus dx. So if I again divide both sides by 2 or multiply by a half, I'm going to state that 1/2 of du is equivalent or the same as x dx. And so the claim here, using u substitution, is that anywhere that I see x dx, I'm going to change to 1/2 du. And anywhere that I see 4 minus x squared, I'm going to change to the letter u. And so our new antiderivative exists from 2 different boundaries, we'll fix those in just a second, of the square root of u times 1/2 du. Well, again, this 1/2 is acting as a constant multiplier, so I don't need that here. I can bring it out to the front. And we now need the antiderivative of the square root of u. Well, we need to find our new boundaries. The new boundaries aren't necessarily the same as the old boundaries, so let's use these numerical values to compute our new boundaries. The upper boundary is simply this old boundary here substituted into our u expression. So we need 4 minus 2 squared, which is going to equal 0. And our lower boundary is going to be 4 minus 0 squared, which is positive 4. And so that's kind of interesting. We're ranging from 4 on the lower boundary to 0 on our upper boundary. This is kind of backwards. But again, that should be okay, because when we compute the result, even though the shape of this object might be different than the shape of this object, the area under the curve associated with this expression will be the same as the area under the curve associated with this expression. I'll try to build that in my TI calculator again. And now before I show the integrals on this, let's just take a note here. This blue graph again is our original function, and you'll notice how when rewritten as the u sub method, the shape of the graph is radically different, no pun intended. The graph of this blue function exists in this kind of S shape, and the graph of our u sub function is this traditional square root graph. Now, our goal was to calculate the integral from 0 to 2 of the blue function, which apparently is 2.6 repeating. And our claim is that the area under the red function, counting from 4 back to 0, is going to be the same. And now I'm concerned that I made a mistake, but let me just finish this, and then if there's something not quite right, we'll fix that. And yeah, this is what I was afraid of. Take note here, this red graph, when we choose a boundary at positive 4 and we integrate to 0, we're moving backwards. And so you might recognize that the area here is the same at 2.6 repeating, but again, because our lower boundary was 4 and our upper boundary was 0, the accumulated change is actually going to report as a negative number. Now, negative 2.6 is not the same as positive 2.6, so let's see where we went wrong. And I think I've spotted the mistake already. I certainly hope that some of you were yelling at your screen while I made this mistake, but I need to point this out here. The function u was 4 minus x squared, so the derivative is not just 2x, but it's negative 2x and negative 2x, and that's going to affect our differential here. That's going to be a negative 1/2. And so that too will change our function in its u sub form. Let's see what happens when we make that change live here. So I'm going to jump into the function itself. That was this guy here. We'll introduce a negative symbol in front and propose those changes. And there we go. This, to me, is good to see. What we're noting is that the area underneath the blue curve is 2.6 repeating. The area under the red curve is still 2.6 as well. But again, we're below the x-axis and we're accumulating our change from right to left. So the negative area below the x-axis, offset by the negative accumulated change moving from right to left, gives us the exact same integral as the original question. And while finding the antiderivative of this blue function might be pretty difficult, finding the antiderivative of x to the 1/2 power, the square root of x, proves not to be quite so difficult at all. So I hope that this video helps illustrate how U substitution can be a benefit to us. When we see each other in class next, we'll spend some time performing some more examples of this and actually solving these integral problems by hand. This video is getting long enough, so I think I'll go ahead and stop here. And if you've got questions on it, please remember to bring them in class when I see you on Tuesday. Thanks for watching.